Question 1. In the diagram above, the two bar magnets are able to create a magnetic field with an average strength of 2 millitesla on the wire over a 3 centimeter region. If the current in the wire is 2 amps, what is the net magnetic force acting on the wire, magnitude and direction? Please pause the video and attempt this problem yourself. So in this image, we can see that the current is going upward, and so the length vector is up, and the magnetic field is going to the left. These two are perpendicular to each other, so theta is 90 degrees, which means that we can use the formula F is equal to ILB. The current was 2 amperes, the length was 3 centimeters, which is 0.03 meters, and the magnetic field was 2 millitesla, or 0.002 Tesla, which creates a total force of 0.00012 newtons. As for direction, we can use the right-hand rule. The wire is going up, so the direction of L is upward, and the magnetic field is going to the left. So if we hold our hand with our thumb pointed upward, and our fingers pointed to the left, we can see that the force is directed out of the page. Problem 2. A railgun is a device that can propel a projectile rapidly with a magnetic force. In the railgun shown, the driving voltage is 500 kilovolts. The projectile has a resistance of 200 ohms, a length of 20 centimeters, and a mass of 3 kilograms. The magnetic field has a strength of 10 Tesla, and the rails are each 30 meters long. How fast is this projectile moving when it leaves the railgun? Please pause the video and attempt this problem yourself. So first, given that the magnetic field is going purely in the z direction, and the rails are going purely in the x direction, and the projectile is purely in the y direction, everything is perpendicular to each other, so we can use the formula F is equal to BIL. Now, magnetic field and length are given, but current is not. To find the current, we can use Ohm's law, V is equal to IR. We have a voltage, we have the resistance. So we can get current is equal to V over R, which, plugging this into our force equation, force is equal to BVL over R. To find the final speed, we are going to need to use kinematics. One of our kinematics equations was Vf squared equals Vi squared plus 2a delta x. If we assume that the only force acting to accelerate the rail was the magnetic force, we can say acceleration is the magnetic force divided by the mass of the projectile, or BVL divided by Rm. We can also assume that the projectile initially starts at rest, so Vi is equal to 0. This gives us Vf squared is equal to 0 squared, which we will ignore, plus 2 times acceleration, which was this right here, times delta x. Or Vf is equal to the square root of 2BVLD divided by Rm. Now, one thing we should be careful about, we have been given two distances. We have been given 20 centimeters and 30 meters. So we need to be careful to understand which is which. In the formula using for the force on the magnetic object, or the magnetic force on the projectile, the L should be the size of the projectile itself. So L should be this L right here. In the kinematic formula, delta x is the distance over which the projectile is accelerated. So it should be this distance right here, which was the 30 meters. Now, ultimately, we are multiplying them together, so if we mix them up, it wouldn't be the end of the world, but it is something that we should watch out for. If we plug the numbers into our formulas, we get final velocity is equal to 2 times the magnetic field of 10 Tesla times the voltage of 500,000 volts times the length of 0.2 meters times the distance of 30 meters divided by the resistance of 200 ohms and the mass of 2 kilograms, which gives us a final value of 387 meters per second. Problem number 3. In the image above, each wire segment is 3 meters long, carries 2 amperes of current, and has an angle theta, right here, of 50 degrees. There is a magnetic field with a field strength equal to 4 Tesla. What is the net force on the wire if the magnetic field is A, acting in the I hat direction, B, acting in the J hat direction, and C, acting in the K hat direction? Please pause the video and attempt the problem yourself. Part A, if the magnetic field is acting in the I direction, which is to the right. The wires, both wires, are in the IJ plane. The magnetic field is acting in the I direction, which is also in the IJ plane. Recall that if the two inputted vectors of a cross product are both in the IJ plane, then the result must be in the K direction. And so the force on each of these segments is in the K direction. For this first segment, magnetic field is going to the right, current is going up and to the right. If we hold our hand so that our thumb is going up and to the right and our fingers are pointed to the right, we can see that the direction of force is into the page. On the second segment of wire, the current is, or the length vector is down and to the right, and the magnetic field is to the right. If we hold our hand so that our thumb is pointed down and to the right, and our fingers are pointed to the right, and this too will be a little awkward, we can see that the direction of force is out of the page. Since, other than direction, the two wires will have the same magnetic force, they have the same length, they have the same magnetic field, they have the same current, and they have the same angle, both will create the same amount of force in opposite directions, and so these two forces should cancel out. And so the net magnetic force on this wire for part A is 0. Part B. Again, both wires are in the IJ plane, and the magnetic field is acting in the J direction, which is also in the IJ plane. So again, the force on these wire segments must be in the K direction. For this first segment, current is going up and to the right, and magnetic field is going up, and so the direction of force is out of the page. For the second segment, the current is going down and to the right, and the magnetic field is going up. If we try the right-hand rule, now here we might find that our thumb doesn't quite stretch that way, but we can see that the result is that the force will be out of the page. For this problem, both forces are acting out of the page, so they will not cancel. And so we will need to find the forces. Both wires are straight, and the magnetic field is constant, which means we can use the formula F is equal to ILB times the sine of the angle. Now current is 2 amperes, length is 3 meters, and B is 4 Tesla. But for direction, we need to be careful. See, this direction right here is given between the direction of the wire and the X direction, or the I direction. But since the direction of magnetic field is in the j direction, the actual angle that we need to use is the complement of the angle given. So this angle given is 50 degrees, so the angle we should plug into this formula is 40 degrees. And since these numbers are the same for both segments of wire, we can just say that the total force is the force of one of them multiplied by 2. So the total force is 2 times 2 amperes times 3 meters times 4 Tesla times the sine of 40 degrees, which gives us 30.85 newtons. And since both segments of wire point out of the have magnetic force pointed out of the page, the net force will be pointed out of the page. Part C. What if the magnetic field is acting in the k direction? Again, both wires are acting in the ij plane, but this time the magnetic field is acting in the k direction. On the one hand, this means that the magnetic field and the direction of the wire are perpendicular, so theta is equal to 90 degrees in both cases. They're perpendicular. On the other hand, each wire will now have force acting in a different direction that cannot be simply added. So let's find the force exerted on a single wire. The force, again, because magnetic field and the direction of the wire are perpendicular, we can use F is equal to ILB. 2 amperes for current, 3 meters for length, 4 Tesla for magnetic field gives 24 newtons. So each wire experiences 24 newtons of force. However, direction. If we use the right-hand rule, for the first segment, the current is going up and to the right, and the magnetic field is going toward us, which means that the force should be down and to the right. For the second segment of wire, the length of the wire is going down and to the right, the magnetic field is going toward us, so the direction of force should be down and to the left. Because, again, there is symmetry to this problem, each of these wires are functionally identical, we can say that in all likelihood, down and to the right, down and to the left, the right and left components, or the I components of force, will cancel out, which means we only need to worry about the j components of force. Now we're going to have to be careful with direction, because the direction of force is perpendicular to this bit of wire, which means that if this angle theta connects to the x, then an equivalent angle theta will connect the direction of force to the y direction, which means the y component will use cosine of theta. Again, there are 2 wires, so we will need to multiply by 2, but this means the total force will be 2 times the 24 newtons on a single wire times the cosine of 50 degrees, which gives us 30.85 newtons and is directed downward.